Hello, my name is Joseph Evans, and I thought I'd run through some of the things I did for my dissertation. So, you can see here, this is my, it's a Google Jupyter notebook in Python. So you can see here, and it's in Google Colab. And what Google Colab is, it's a service provided by Google where you can sort of just run Python notebooks on their servers for free, which is very nice of them. So we can connect up here. We can make sure our runtime is using a GPU and begin. So this is sort of a demo. It's tied into my dissertation project where I did emotion recognition in speech. So let's get started. First things first, we import our different libraries. So there's a few different libraries here. We've got TensorFlow, we've got Class, which is an API for it that makes it pretty easy. Librosa for audio processing. We've got our pyplot, NumPy for big arrays of data. And the dataset we're going to be using is CreamerD. And in my research, I sort of focused on the different datasets, and I found CreamerD is really the best one that's easily accessible. It's massive, that's the thing. 7,000 clips from 91 actors, which is very useful because it's quite a diverse range of people. So lots of stuff to train on. So we use Kaggle. We use Kaggle to download this dataset, and you can run this yourself if you want. So basically, all we need to do is create a Kaggle account. We need a basically what do they call, like a token, so we can access the API. Let me just find that. It's here. I can drag that in there. And running this simple exclamation mark runs a command, so that'll download our dataset for us. See, it's going very quickly, as it's all done in the cloud. And get that dataset path, we can check that it worked. 7,442 samples, same as this, which is correct. We can also mount a Google Drive as well. That's something that it makes very easy. Just give me a second. So I'm connected to my Google Drive account. That means we have some persistent storage. Otherwise, all of the we wouldn't be able to save anything permanently, and it would all get deleted when we close this tab. Because of course it's cloud computing, like a little temporary thing that Google makes for you. So that's connected. You can see it up here. My drive. I've got some different folders in it. And let's go into some of the pre-processing that you sort of need to do for this. So the first thing first is we need to load a one of the files. So we just go in here. You can see the label is found in the name of the file. So this is the speaker number. That's like the sentence they say. That's the emotion, and that's the intensity of how they said it. Out of that, we get we load it using Librosa, just passing the path. We get our signal, which is the data, and the sample rate, which is how many samples a second the audio is in. Makes sense. So we can actually just plot the data using pyplot, and you can see we've got samples and amplitude. So the sample rate is about 20,000, just a bit more. So roughly 2 to 3 second long clip here. Now we need to define some values, because we're going to turn these into mel-log spectrograms. On mel bands are like filters. They take a specific like section of like a wavelengths and turn them into like one single data point. So each mel band, we have lots of mel bands. In this example, we have it set to 128. So across the Fourier transform, there's 128 bands, and that creates a Y resolution of 128. And we also have this hop. That's how many times it goes along a signal. So we go along 64 times, doing fast Fourier transform each time, and each time we take up 512 samples. So the number of hops defines our x-axis, the number of pixels in our x-axis. And then we're actually going to split this clip into multiple same length like child clips. So one parent clip, multiple child clips, and the number of hops basically determines how many well, all this stuff does. We can actually, there's the number of samples per clip will tell us how many samples or how many child clips there will be from one clip. I call oops, sorry, SR equals sample. Wait, a bit of a spelling mistake. There we go. So here, on the clip that we loaded, which is this one, you can see we've got 16,000 samples per each clip. So we're going to take a clip, child clip here, a child clip here. So for a total of 3 clips, each clip duration is about 0.7 seconds. Giving us this resolution. And again, the x-axis is the number of hops, the y resolution is the number of mel bands. So this code here, it'll segment our big parent clip into multiple child clips, or sometimes I call them samples incorrectly. As you can see, these red lines sort of define 1, 2, 3, and that's how it works in the when we process the whole dataset. We actually split it up, and we can plot mel spectrogram and a log mel spectrogram. So we apply the logarithmic scale, and you can see that the data at the bottom is a lot more sort of vivid, and we can really start to see the patterns just with a human eye. So along the axis, 128, 64, and we can actually go in and like if we sort of change these settings, I don't know, let's say 16 and let's say 32 hops. We run that, we run that. You can see we have loads of clips now, and the resolution has changed quite a lot on our clip. So there's lots of different ways you can actually choose to put your settings and pre-process data, which sort of adds to the complexity of everything. Let's change those back. There we go. So that's just a little example of how each clip in our dataset will be pre-processed into a log mel spectrogram, and we will feed those log mel spectrograms with the label into our machine learning algorithm. In this case, it'll be a convolutional 2D neural network, which I'll show in a second. So here we actually get on to preprocessing the whole dataset. And here we've got a couple arrays. We've got the sentences, and you'll see this is part of the name of the file, and each of these are part of the name of the file, each of these. And here are those settings again. You run those. These are just constants, because they'll always be the same. And we'll skip this for a second. And this is the code that will preprocess our dataset. What we actually do is we, well, in this example specifically, is there's a dictionary of parallel arrays, and when we split up this into its clips, well, child clips, each index will be one of the child clips, and that will share the same information as the same labels as its parent clip. So if I was to access index 4 here, that would be the same as index 4, and it's done this way, as this is sort of the way you'll feed an entire array into a class, and you'll have your parallel x and y arrays. So here, for every file in our path, we're going to split it. We're going to get rid of the end part. We're going to split the speaker, sentences, emotion level, because that's all, remember in the file name we had, first of all the speaker number, then the sentence that they say, then the emotion, which is what we're interested in most, and the emotional level. If any of that's incorrect, we discard it, and we use that code to create child clips. And for each child clip, we append the information. We'll create a log mail spectrogram, which we append specifically here. Was all of these details will come from the parent part. Only this is the function that comes from the child part, and that's the actual data that we care about, the X data. So this would take quite a while to do. So instead, we're just going to, at the end, you can save it here, and this will just save to my drive, my Google Drive, and I can load it from my Google Drive. This is also going to take a second, but here's going to be our spectrograms dictionary, and it's loading. You can see here spectrograms. It's called .pickle, and that has loaded, and I can prove that. Here's just a little function. We can grab indexes from spectrograms, and you can see we're just getting each array and getting the same index from each array, each parallel array. So you can run this for 30, and we'll get a different one. And you can see all the information. Part 0 of clip 10, where speaker 1076 says IOM was angry at level XX. So there we go, we got our dictionary. So next thing is the model. And I did quite a lot of testing in my dissertation on different ways to build a model for this. And I found generally a model like this worked best for what I was using it for. I mean, it's going to change based on how you actually create each spectrogram. You know, what kind of model you're going to want. But this one, it hasn't really been fine-tuned for this little demo, but it's kind of unique in that it doesn't really have dense layers at the end. We've just got our convolutional 2D layers, followed by max pooling, followed by dropout. Quite similar to how other ones would do it, just without the dense layers. So you can see they're actually just increasing in size as the filters. And at the end we have our classification layer, and that gets compiled, and this is written in a function, so we can just create a new one wherever we like, and run that. Okay, so in this example we just create a standard train test split in the data. So we take a portion of the samples for training and a portion of the samples for testing, and of course the model won't have been trained on the testing ones. So here we've got that emotions. Those will be our classes. So we're going to have 6 classes. They're going to be angry, happy, sad, etc. And to prepare, we're going to start using NumPy. So the X data is just turned into a NumPy array from a standard Python list, and that'll be shaped into this specific shape, as that is again we've got a Y and X. We also prepare Y. We change it to one-hot encoding, or categorical, which means it's sort of like in a binary sort of way of representing it, where class 1 would be class 0 would be 1 0 0 0, class 1 would be 0 1 0 0, class 2 would be 0 0 1 0 0, etc. And we append that to a Y data array. So you can see we've got 4 arrays here, 4 arrays where train X and train Y are parallel. Here we're just keeping the index the same. Train Y index is parallel to train Y one-hot encoding and train Y numerical. And that sort of allows us to take a closer look at the results once it's all finished. So the main ones we're going to look at are the train X, test X, train Y one-hot encoding, test Y one-hot encoding. And we will be able to print that out to show they're sort of parallel. So here's some information. You can see train X, train Y, they're both the same number. Here you can see our resolution, and test X and test Y are the same as well. And we can see the sort of process as we grab the index of a clip, we get the label, we turn that into a numerical digit, which will be our numerical array, and then we turn that into one-hot encoding. That's what one-hot encoding looks like. Now we actually train the model. It really is as easy as this, a single line in Keras, which is very nice. So we use our function here to get our model. Here's the batch size, here's the epochs. So we're going to do 20 epochs, which isn't very many to start. And we've given our test data as our validation data, just for sort of demonstration purposes. Obviously you probably wouldn't do this if you're actually fine-tuning the model, but I think it's okay here. So I'm going to start running this. And thanks to Google Colab, it does the GPU setups for us, which is quite a complicated process. And it will actually run pretty quickly. But after the first couple epochs, I think I might pause it and then start it up again. It's just going to take a second to start up. And yeah, it's going to train our model to predict our emotions whenever it wants to start. There we go. So we've got a couple of numbers here. We've got our loss, accuracy, which is probably the most interesting one, and our validation accuracy, how well it did on the validation data. Interestingly, it's scoring better on the validation data than it is on the test data, but I shall come back when that's finished. There you go, nice and quick. You can see, as expected, the accuracy on the training has overtaken the validation set. And we can start plotting some graphs. So when the model trains, we save a history, and that tells us how accurate and the loss over the epochs. It basically just takes this value and stores it in an array, basically. Something that's a bit like an array. Let me just plot that, and we can see it's getting more accurate over time. Accuracy is pretty low, but it's important to remember this is a little short 0.7 second clip, and not all of them are really perfect for this sort of stuff. A lot of them are sort of like a little short starts of the clip where there isn't much data. So the total accuracy comes to 0.355, which is better than random. Random is 1/6, so it's like 1.666. 1 divided by 6. So that would be the random accuracy, and if we beat this, we know the model is actually doing something and making better than random predictions, right? So that's working, and we can actually show here that we basically predict all of the test text data. We get our predictions, and that when it outputs a prediction, it's basically an array of the 6 classes, and whichever one has the highest number will be the one that it is most confident is the actual emotion. So when we call argmax, we just pick the value that was the biggest, and then we compare both of those to create an array of true, false, false, true, 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 false, on whether the prediction was a success. And then we can basically just divide to find the accuracy, which is the same as the one shown in the previous code. So if you wanted to sort of make a prediction on a new clip, you could pre-process that clip in the same way, such that the spectrograms it produces are the same resolution and it's labelled properly, and then you could run it into model.predict and get the argmax, and you would be able to classify the emotion. That's how you would implement it in an actual piece of software. There's also some other things. I might get into that later. One more thing with the random chain test split one. I've just created some more code here. Basically, we'll see how the model did for each of the actors. So we've got 91 different actors, and let's see on this bar chart, you can see this is the accuracy for each of the actors, and you can see the model was able to make predictions on some of the actors more than the other ones. If you kind of look just below, like what is it, 38 or something, nice tall red one, we've got a over 0.6 accuracy on that person, whereas other ones scored like a 0.3 accuracy. So the model was able to predict better on some actors than others, which is pretty interesting. Another bar chart here. Instead of different actors, we take a look at which emotions it was able to predict better, and you can see emotions like angry and sad. It predicted very well. It predicted sadness in almost 70% of the time. And you can see how angry and sad kind of stand out if you sort of think about it. Like it's quite easy to tell when someone's angry. But other ones you can see are like neutral, happy. Surprisingly, fear and disgusted are very, very low. I would even say disgusted is getting near that random accuracy point, perhaps below it, which is very interesting. So, we could use something like this to like test. Maybe we wanted specifically to test for fear. We could design our model a bit differently. Perhaps we could do something to the samples, pre-process them slightly differently, and see if these sort of bars change. Just some of the sort of interesting things you can do, and this is why we saved all that metadata from each of the clips. We could also do this for the emotional level and the specific phrase they were asked to say, but I've not done that. So let's move on. So here's the next part of this notebook. It's basically, instead of just doing a train test split, which will just take random samples from the dataset, which is all just sort of jumbled together. So it would have trained on actors that it's going to predict on. So it'll know their sort of. It might find patterns that sort of suit that actor very well, and then make a better prediction. In this version, under the part under this title, we actually separate it by actor. So we put a portion of actors it trains on and a portion of actors it's never seen before, and it's going to test on. And we pre-process it slightly differently. So instead, we, in the dataset, I should say, it usually goes male actor, female actor, male actor, female actor, into how they identify the gender. So I think there's about 1,090 this goes to, and it just cuts off past 1070 here, and we can see how many samples we'll get in the end. It's about the same as the last time, but split by actor instead of just randomness. When we run this, you can see we get about the same size, which is just by changing this number. That's all the same, and we can see the speakers here in the train data, just a random selection, and a random selection in the test. And we can see the Trainiac speakers, none of them are above 1070, and all of these ones are above 1070. So we know that they've been split properly. Once again, we can run this, and it's using the same variables from before, the same epochs, the same batch size. So it's going to run 20 times, 128 batch size. I'll be back when it's done. So that's done. Let's take a look at the accuracy. So we get a slightly better accuracy, which is kind of strange. It just goes to show the different ways you can sort of mess with arrays and things, and I've just loved using Python to mess with big arrays and things. It just works so well, and the libraries you have it for NumPy, it's just amazing, and it's a real pleasure to sort of create a good graph. I love creating a graph using pyplot and just plugging in your arrays, and it just appears in this lovely beautiful graph. So yeah, that's sort of an example of what I did my dissertation on. How you can see sort of how it sort of focuses on audio, spectrograms, using datasets. Datasets was really the focus of the dissertation, and comparing how a model that was trained on one dataset would perform when tested on a different dataset, so a dataset it's never seen before, and that produced some quite interesting results. If you go on online and you look for these speech emotion datasets, you find quite a few, but I didn't really find too many papers comparing them. So I thought, oh, there's something I can do, and hopefully contribute something, even though I don't really have a whole career's worth of experience in this. But I'm really happy I chose this subject for my dissertation, as it was incredibly interesting. You learn about all these new technologies. You need to understand the sort of basics behind how these new machine learning things work, and you just find out it's all about mathematics at the end of the day, and it's no magic involved. But learning about signals, learning about using Python, and this sort of made my Python my favourite language, because I had to spend so much time learning about it, and just manipulating data and spectrograms and all that kind of stuff. Made for a really interesting and fun to do dissertation, and it really motivated me to do quite well in it, I think, because it was always interesting reading a source and learning something new, even if it does frazzle my brain sometimes. So thank you for watching. I'm Joseph Evans.